predicted to have some superconducting states. This was back since close to its discovery. So basically, when I started my PhD around 2007, there were already talk that graphene might be superconducting, but most of the time, what we found is that actually it behaves, its electronic behavior is really mostly well described by single particle picture. And then basically what happened was a revolution introduced by Pablo Herrera at MIT, who in 2018, all of a sudden, unexpected to everybody, showed that two graphene layers, if they're twisted in the right way on top of one another, they can actually start having strongly interacting electrons. And his first work was on correlated insulator behavior at half-filled graphene devices. Then nearby, he immediately also observed that these same type of devices can be superconducting. So he observed strong correlated insulators and a superconductivity close to it. And then actually the story continued, and the system became even richer last year, where several groups reported that also these systems can be magnetic. So this was in particular reported by David Colin-Gordon from Stanford. And then this magnetism also would introduce some topological states, and anomalous quantum Hall was also discovered very soon after that. So, and basically, we now have a system which has all these emergent phases. All these phases can live in this very same device. So basically, we can gate tunably tune between different phases and observe them all at the same time. And so basically, what I'm going to talk about is along the lines of the physics which arises in the system. So I'm going to give a quick introduction of marine materials and twisted bilayer graphene and how all these phases come along. Then I'll talk about some transport work by my own group, where basically, as I mentioned earlier, we observe superconductors, correlated insulators, magnets, and churn insulators in one and the same devices. And then last but not least, I'll maybe talk about some quantum sensors for anybody who's interested in quantum applications from these materials. Okay, so just really broad introduction. So really the field started in 2004 when under Game and Kosta-Novoselov realized that you can extract two-dimensional sheets of graphite from bulk graphite. And this basically introduced the notion of graphene, which is basically just a two-dimensional plane of graphene of carbon atoms. And these graphene layers were quite stunning because they were extremely high quality. You could study all the physics in the 2D limit, which you were known from gallium arsenide, so you can study quantum Hall effect and things like that. Then also those layers were different if you have a single layer or bilayer or tri-layer systems. So those are completely different electronic band structures. We could control the system with electrical fields and magnetic fields very easily. So basically graphene was quite interesting. And then the other thing which we also realized very quickly is that it's really not just graphene and graphite which can be manipulated in this way, but there are really a lot of different materials which can be extracted in the single layer. And these really cover all the interesting phenomenology. So this includes superconductors, semiconductors, magnets, topological insulators, and so on. And so the other thing which happened in the field was also that we realized that we can actually build up from these materials. So we can actually extract those two-dimensional layers, but we then actually can also combine them into the third dimension. So this just illustrates the process we do. So basically, we can exfoliate layers of graphene, which is sort of this two-dimensional sheet which sits on a substrate, and then we can stamp it with hexagonal boron nitride layers, which are basically the insulating form of graphene. And we can basically, with this process, we can assemble them one on top of another. And in the end, we really end up with these heterostructures, and we can assemble them one after the next. And basically, so what this gives us now is an opportunity to really, starting from those two-dimensional layers, assemble any type of combination of material we like, and we can, in principle, assemble insulators, metals, superconductors, ferromagnets, and we can assemble them in these stacks. And while initially, when this work was done, I think very few people would have bet that this would work so well. But really, TM cross-section measurements of such stacks, they revealed really that the interfaces between these materials are extremely good. And really here you can see that between HBN, graphene, and MOS2, you really find really atomically sharp interfaces. And last but not least, of course, the Moray superlattice. This is a really a novel, relatively novel concept in heterostructures, is that actually all these layers, we can assemble them on an arbitrary twist angle between each other. And I really want to contrast this with other heterostructures which were developed over the last years. So of course, everybody knows molecular beam epitaxy. This exists since the late 70s or 80s. And basically, it was possible in very complicated machines to sprinkle atomic species onto one another. And basically, by changing the atomic species one sprinkles, one can actually assemble layers upon layers upon layers of different material species. The problem with molecular beam epitaxy is, however, that each grown atomic layer inherits the crystallographic orientation of the previous atomic layer. So basically, the twist angle is locked into place, and really we can compare it with Lego, where you really lock layers into place. And this is really different here with these van der Waals materials, because we don't start with atomic species and single atoms, but we start with already well-formed two-dimensional crystals. And that really means that we can now really rotate these layers with an arbitrary angle, and we are not locked anymore to the crystallographic orientations. And this really is the enabling property which allows us now to perform these Moray heterostructures. And just to really, in a slightly more detail, to explain how twisted bilayer graphene works, basically we start with a single graphene sheet. And again, this is, as you can see, this is this hexagonal lattice of carbon atoms in 2 dimensions. For such a lattice, we can perform simple tight binding calculations, where basically the band structure is defined by the 2 A and B carbon atoms, which define the unit cell. And we can just define a hopping term between A and B lattice sites, gamma 0. And solving this tight binding approximation in the low energy limit really gives us this linear band structure. And that just means that graphene is a semi-metal, or in other words, a Dirac metal, and electrons behave like massless particles. And this is, again, all well known from graphene. But again, what one can do is one can actually look at also bilayer graphene. So what happens if you have 2 perfectly aligned graphene sheets? So basically, this is how naturally occurring bilayer graphene looks like. So we call it the AB bilayer graphene. And you can really think of it as two carbon sheets just basically on top of another. And as you can see, so if we look now at the band structure calculations, what we need to do is first of all, we have now a more complicated unit cell. So we have now 4 carbon atoms in the unit cell, 2 in the bottom layer and 2 in the top layer. And we, of course, have now many more hopping terms between those layers. And what this gives us now, if we do the tight binding calculation, this gives us now 4 bands. And these bands are actually not Dirac-like anymore, but they're hyperbolic. So basically, close to 0 energy, these can be approximated with a parabolic dispersion relation. And what I also want to mention, so I have shown here only 1 valley, but in general, graphene has 2 valleys in the K and K prime points. And basically, we have additional to spin, we have another degree of freedom, which is valley. So graphene is 4-fold degenerate. And so, as you can see now, so what happens if we now do the trick and we now just randomly twist one layer on top of another, as you can see, so sort of this explanation which I gave you for AB bilayer graphene, this completely stops working, because now all these hopping terms between the top and bottom layer, they're basically screwed up. They're basically oscillate with this superlattice which is formed, right? So the superlattice, again, between the two layers, we call it the Moray superlattice. And one way to approximate this Moray superlattice is approximated with AA stacking regions and AB stacking regions. And you can basically see here the AA stacking regions are the regions where the top and bottom lattices are perfectly aligned. And AB stacking regions are the regions where one of the atoms in the top layer is exactly in the middle of the hexagon of the bottom layer. So this is a little bit slightly shifted lattices. But of course, this is the transition between AA and AB in this Moray superlattice is periodic. And basically, this oscillation of the hopping parameters, this gives a strong renormalization of the entire band structure. And I also want to mention that the unit cell size, so I will talk about magic graphene. Magic graphene is the twist angle, where the twist angle is exactly 1.1 degrees. This is where the bands become completely flat, and I will talk about this in a second. So the unit cell size is extremely large, so it's 14 nanometers. And you can compare it to 10,000 atoms in the unit cell. So we really deal with an extremely huge unit cell. Okay, so and the other thing is, of course, these things are not just on paper, but we can actually really image these. So this is here. This is shown a typical scanning tunneling microscopy measurement of some of our devices, which were performed in Milan Allen's group in Leiden, and they really can image those periodic Moray superpotentials, and really we can find that these are quite periodic, stacked along the device. And really, these periodic structures, which you see here, those are not individual atoms, but those are really the individual Moray lattice sites. Okay, so and as I mentioned, so what happens now with the band structure? So here we have now calculated the band structure for 1.3 degree device. And as you can see, sort of, if we look at the band structure now, it still resembles the band structure of twisted bilayer graphene. Of AB stacked bilayer graphene. So we still get those two bands, which are what you can sort of guess that they would develop hyperbolically. But what happens is now that instead of those two bands running smoothly across the energy spectrum, we actually see strong renormalizations happening, and these renormalizations lead to band gaps appearing in the spectrum, and for certain twist angles very close to 1.1, we also see that some flat band regions, which are very isolated from the rest, can appear. And this, again, this is also not just theory. So we just have a paper which should appear next week in Nature Physics, where we actually were able to study the energy spectrum of ARPAs. This was done by the Felix Baumberger group, and really we can resolve many of these features, the flat bands, the energy gaps, and also the Fermi surface reconstruction. Okay, so and this sort of renormalization, this is really continuous as a function of twist angle. So basically here we have done some calculations to demonstrate this, where we basically plotted the density of states of twisted bilayer graphene as a function of twist angle. And what we typically find is that the twist angle, when the twist angle becomes lower than 2 degrees, really the Van Hove singularities, they approaching 1.1 degrees, they sort of diverge to each other. So that means that, in other words, the bands become extremely flat, and really somewhere close to 1.1 degrees, we see extremely flat bands. And these flat bands, of course, have extremely high density of states. And this density of states in reverse then means that interactions can be quite strong in the system. Okay, so this is now just like a typical band structure, which we usually use now. So really zoomed in and all of this, we have those flat bands. they're isolated by energy gaps to the higher order bands. The bandwidth is very, very small. It's around 10 MeV. And I also want to remind that really in graphene, we have spin and valley degeneracy. So we have 4 electrons. So we have 4 degenerate electrons, spin and valley. And in return, what it also means, of course, these flat bands, what they mean is that we also get maximally localized one-year orbitals. So in other words, flat bands mean just that the energy, that the kinetic energy or the Fermi velocity diverges to 0, and the kinetic energy also diverges to 0. And that means the electrons like to almost stay in place, and therefore the kinetic energy is small, and therefore the Hamiltonian is dominated by now interactions. And really, those maximally localized one-year orbitals, they have their they have this shape, and they have their maxima in the it's really in the moire, in the center of the moire itself. Okay, and this is really where all the predictions started to happen. So we have now a system which quenched kinetic energy, we have dominant interaction energy, and therefore all these predictions for multi-insulator type physics started to happen, where the necessary condition, of course, is that U is just much bigger than T. Okay, so now I'll move on to some of the more experimental results. So just to give you an idea how the devices look like, which we make in our lab. So usually this is an AFM image of a typical device. So we shape those hole bars of magic graphene. And what's important also is that these hole bars, they really consist of a quadruple layer of van der Waals materials. So we usually have a graphite layer underneath it all. In graphite, we just treat as a metal. We have HBN, which is just an insulator, and we have encapsulated in this HBN this twisted bilayer graphene. And so what's important now is that really the graphite gate we can use for different tricks, and I will talk about this in more detail later. But really what we can do with graphite is we can apply a voltage to the graphite, and then we can just capacitively change the carrier concentration of the twisted bilayer graphene. And that the capacitance is strong enough that we can actually completely empty and completely fill the moire bands just by tuning a voltage. Okay, and another thing I want to say is that one of the challenges in this field was also to make homogeneous twist angles across the whole device, because you can imagine that in an assembly process like that, the twist angle might vary a lot. And indeed, so this is really true. So you have to understand that graphene has a mechanical property of a Saran wrap. So basically, if you try to glue 2 layers of Saran wrap one on top of another, you have to really be very careful to align them. And very often you find faults, you trap bubbles, and all the properties you can think of when you wrap a sandwich. So in our lab, we were able to really develop a process which kind of reduces this wrinkle formation. And really now we have devices which are relatively twist angle homogeneous with a twist angle below 0.01 degree over 10 microns. Okay, so, and what we do really in our lab, we just make those devices and then we measure transport. We measure just resistance as a function of temperature, as a function of magnetic field and carrier density. And I want to really show a typical measurement which we perform. And so again, we just measure resistance, really, the resistance of the device. And then what we also do is we change the carrier concentration by tuning the gate. And what it means really is that we can start with a band completely empty. So we can start at this limit here where the carrier concentration is negative. And this region here, we find a very strong insulator. So resistance is goes to the mega ohm. It's really insulating. And we explain this position as the band gap, which we observe in the band structure here. Then the vice versa happens if we completely fill now the entire band. And now again, on the other side at positive charging of the full moire bands, we also observe a band gap. Then in the center here, we observe a drop point. This is basically the point where those 2 gaps sort of touch. And all these features are really explained by the single particle band structure. So we can really look at this band structure and explain all these features here. Except, as you can see, there's really much more going on. There's actually now many more resistance peaks here. So we observe resistance peaks here, here, and there, and also the same on the whole side. And actually, we look closer and we convert the carrier density of these resistance peaks to electrons per unit cell. Then we find that these resistance peaks appear all at exactly 1, 2, 3, and so on electrons per unit cell. So these resistance peaks are not random, but they're really well defined, coinciding with integer fillings integer fillings of electrons or holes per Murray unit cell. And so these resistance peaks are absolutely not explained by the single particle band structure, but these really have a different origin. And currently we all believe that they have to do with correlations and basically with electron interactions in the system. And the way we think about it is really in the mod insulator picture. So basically, we think of individual atoms per Murray unit cell. And basically, what we need to sort of account for is we can imagine that one electron can hop between different lattice sites. And so the hopping term or the kinetic energy is T. And of course, as I mentioned, T is very low in twisted bilayer graphene. So T can be neglected. And the other parameter which is important is, of course, U. This is the energy cost which you have if you have 2 particles per lattice site, or basically this is the Coulomb energy between the 2 particles. And so what happens really is that if our bands are partially filled, then electrons can just hop between lattice sites. But whenever we get to the condition that we have really integer fillings of electrons per unit cell, so again, integer fillings here can be 1, 2, or 3 because of the 4-fold degeneracy. Whenever we have such a condition, it costs a lot of energy for electrons to hop between different lattice sites. And what happens is that we basically obtain an insulating gap, and this insulating gap is due to the interactions. And I want also to mention that because we have all these conditions, we have gaps developing at 0, 1, 2, 3 electrons per unit cell. Of course, that also means that for example, 1 or 2 or 1 or 3 electrons per unit cell, somehow the bands have to break some of the symmetries. So they have to break either spin degrees of freedoms, they have or valley degrees of freedoms. And so in principle, since the beginning of the field, there was a huge debate whether some of these correlated insulators could be valley polarized or spin polarized, or in other words, magnetic or some of those scenarios. Okay, so those are the correlated insulators, but also I want to really put this a little bit in perspective, and I want to really put this in perspective in terms of other correlated insulating systems which have been observed before. So of course, mod insulators were observed in normal crystals. So for example, in the cuprates, here because everything happens in the crystal lattice itself, the lattice spacing is of course much smaller. It's in the orders of angstrom, and therefore of course the Coulomb energies is much higher. They're in the order of eV. The other known system to form mod insulators are of course optical lattices. Here the unit cell is much bigger. It's in the order of microns, and the interaction energy is in the order of picoelectron volts. And then really now twisted bilayer graphene is somewhere in between. So it has a much bigger unit cell than crystals, but smaller than optical lattices, and therefore also the interaction energy is somewhere intermediate. It's in the order of millielectron volts. And I will talk about it in a second, what kind of new possibilities this opens up. Okay, so, and one thing I didn't mention when I talked about the insulators is actually, as you can see, so the insulators are the regions where we have really high resistance. So basically, as you can see, so here the resistance goes more than 2 mega ohms, but then in between a lot of those insulators, we also saw regions where the resistance basically drops to 0. And so if we now take a temperature dependence of the very same data, we actually find that indeed those regions of zero resistance are superconductors, and those superconductors basically live in between the correlated insulators. So really here in such a phase diagram which we draw, so the red regions are resistive regions. So again, this is a color plot versus temperature. And you can see, so the red regions are the regions where we still observe the correlated insulators, but in between, flanked in between the insulators, we observed many superconductors. And these superconductors, we usually, just to convince you, usually verify by really measuring R versus T and observe zero resistance. We also measure critical current. So we measure DVDI as a function of critical the bias current, and we observe that really there's like a critical current, which critical current transition, which is consistent with the Brzezinski-Kosteles-Talos transition. And I think the best proof right now for superconductivity is that because of disorder in the devices, we also observe Fraunhofer interference patterns. So we really observe Josephson junctions in that system. So, okay, so, and I really want to take a second to contrast a little bit this type of superconductivity. So first of all, of course, we have now a situation where we have a correlated electron system, and we have superconductivity originating from it. And of course, the immediate comparison, also looking at the phase diagrams, were that with other unconventional superconductors, like the cuprates, of course, but also like the heavy fermion systems or the pnictides. And really, naively speaking, the similarities are big. So also, like in the case of cuprates, we get mod insulators without doping, but when we dope the mod insulators, we get superconductors left and right. And this is really somehow reminiscence of the phase diagrams we see here. And the other things, of course, which were immediately intriguing is that also the carrier density at which from which this superconductor is formed is somehow record low. So here we made a graph where we contrasted the carrier densities for typical superconductors, and as you can see, graphene, magic and graphene is by far the thinnest superconductors in existence, but also it has a carrier density which is orders and orders of magnitude lower than in conventional superconductors, but also much lower than in high temperature superconductors. So it's really an unusual superconducting system. And for this type of low carrier density, graphene also has still a relatively high TC. So right now, the record TC is around 5 Kelvin. But compared with a carrier density of only 10 to the 11 electrons per centimeter squared, this is really outrageously high TC. So currently, there is a big sort of debate how to interpret the superconductivity. Could it be unconventional superconductivity? Could it be more conventional superconductivity? Now, I will also maybe mention that we also observe a lot of topological states now in twisted bilayer graphene. So there's now a recent sort of debate is also that these states could be topological superconductivity. So I think, yeah.
Can I ask a question?
Sure. Yeah.
This I mean, an observation. When you say that the superconductivity occurs at a very low carrier density, so that is to be expected, right? I mean, because the superconductivity is happening due to these more superlattices, right? Yeah. Not because of the underlying graphene lattice. And simply because these more superlattices, their effective lattice spacing is so large, you don't need the point I'm trying to make, I guess, is that it is not the electrons which are participating in superconductivity, right? It is quasi-particle excitations, right?
Okay.
And these quasi-particles live on the more superlattice, right?
Okay.
So you need, let's say, one of these quasi-particles per superlattice site, or something like that for superconductivity, right?
Mm-hmm.
Your effective carrier density. So in terms of the underlying electron carrier density, that can be a low number.
Yeah, so I think right. So I think I would just so I think that is all true. I think what is unusual really. So I mean, I think what you're saying is true for any system, right? I mean,
Yeah, right. I mean,
yeah.
yeah, I mean,
So, but I think the unusual part is that usually the lower the carrier density is, the lower the Fermi temperature is, the lower the TC in materials. So people have looked at so also like just if you look at this graph here, usually you can see that if I would look at the TC of all these materials, usually the TC scales with the Fermi temperature. So it's very unusual that actually you get an effect like superconductivity actually originating from such a low electron density. So the electron density is low because of the things you said, because of the Moray lattice and all the arguments you gave. The surprising thing that you wouldn't expect probably a normal superconducting mechanism to necessarily give you a sizable TC under those conditions.
okay.
So usually, so really, if you look at it, all these materials which are close to graphene here on this axis, which have also low carrier densities, they also have exceedingly low TCs.
Okay.
Question, please. What is D?
D is thickness.
Can I also ask a short question? You had in one of your previous slides correlation lengths, coherence length psi.
Yeah.
What is the relation between these coherence lengths and lattice parameters and average distance between electrons?
Sorry, so Xi we know because we did critical field measurements as a function of temperature and just did Ginzburg-Landau. And so from this, we extract a Xi of about 50 nanometers. And
what is lattice parameter?
Yeah, lattice parameter is 14 nanometers. So it's 3 times the lattice parameter.
Could I ask my question again, please? What is the D?
D is thickness.
Thickness of what?
Thickness of the material, of how thin you can make the material.
Aluminum, but these are bulk materials. Okay, well.
Yeah, so I think right. So the aluminum, yeah, exactly. So aluminum, if you prepare it in 2D films, if you make thin films out of aluminum, I think you can make it maybe a 5 nanometers thick or so. That was the point here.
Okay.
And the graphene, you can actually, if you look at the thickness, is 0.6 angstrom. It's 0.6 nanometers, so it's 10 times thinner than the thin film limit of aluminum.
Thank you.
Okay, so but I want really to mention what I think what's important here is that right now I think if you look at published papers reporting superconductivity in magic graphene, those are maybe 5 papers. So I would say that we still at the early stage. We still have more questions than we have answers. I think there was a little bit of an oscillation in the community whether we really think it's conventional or unconventional or maybe topological superconductivity. So I think it's still an open field, and I think the debate is still quite active. One thing though, one experiment I want to show though, however, really deals with the new possibilities, which I was explaining before, is that we really have this lattice constant of which is sort of intermediate between crystals and optical lattices. And so, for this, I just want to go back again to the mod insulator picture. And basically, what in this mod insulator pictures, again, the two relevant energy terms are T and U. And basically what we can do is in graphene, we can tune both of them. So T, as I showed before, this is the kinetic energy is just related to the bandwidth of the flat band. And the bandwidth of the flat band is a function of the twist angle. So that means we can slightly increase T by making the twist angle slightly bigger or larger than the magic angle. So we can actually tune T. And then the other thing is, which I mentioned, so and this is really this graph here, right? So this is, as I mentioned, really the bandwidth, which is kind of defined by the spacing between those density of states peaks. It is really tunable. So a twist at the magic angle at 1.1 degrees is really minimal. But then if you go slightly away from that angle, you see the bandwidth increases and therefore T increases. Then the other thing is really U is also tunable. And as I mentioned, basically, if you look at the cross section here, right? So we have a really complicated dielectric environment. We have these insulators, HBN. We have this metallic graphite, which is very close to it. And therefore, basically, this allows us to change the dielectric environment and actually also introduce screening layers to the twisted bilayer graphene, and therefore we can change U. So bottom line is, it appears possible that we can just change this U versus T ratio and then see what happens to the correlated insulators. And actually, this is what we did. So this is a recent paper where the theory was done by Leonid Levitov at MIT. And basically, we just were wondering, so what is the characteristic length scale of the lengths of the distance between the graphene and the graphite gate, which we need to make in order to have a screening effect. And basically, the screening effect would just look like that. So basically, this is the magic angle graphene superlattice, and the red regions is basically the Vanier function. And the Vanier function in graphene is extremely big, so it's 15 nanometers, right? So it's just the size of a unit cell. And what we have found is that if we bring the graphite gate close enough to the graphene, that it's the distance is smaller than the size of the unit cell. So that means whatever distance is smaller than 15 nanometers, really the graphite starts effectively screening out the electrons in the magic angle graphene lattice, and it really therefore strongly reduces the U. And what the calculations are giving now, so again by Leonid, is that really this U parameter as a function of distance of this graphite gate to the magic angle graphene, it really can be treated as completely unscreened whenever the distance is more than 30 nanometers. And this is actually, before this work came out, this was actually pretty much the thickness people have used. But then if you reduce the thickness, the spacing here, if you reduce it to below 15 nanometers, you can see that U dramatically changes. Okay, and this is really, I want to contrast these explanations with our findings. So we have made several devices which have all varying distances to the graphite gate. So the lowest device here, this is a device which is a dead-on magic angle, and it has the thickest HBN thickness. And really, in this device, what is really important is that we really get those red regions, which are those resistive insulating regions at integer filling. So again, here at -2 electrons per unit cell, at +2, at +3, and even at 1, we get really correlated insulators, and the correlated insulators are interrupted by are not interrupted by the superconductors. And if we go now up to device 2 and device 1, what happened here is we slightly detuned the twist angle to smaller and larger values. So we changed T, we increased T, and also we went to thinner HBN. So here HBN is now 7 nanometers. And what we really find, and this is really visible here in the top phase diagram, is that we don't see those correlated insulators anymore. So for example, here we would expect a correlated insulator. At -2 here, we would expect a correlated insulator. These are gone, but strikingly, the superconductors are not gone. So the superconductors are really still there in the data. Actually, if we now look at the intermediate layer, then we can actually see how one of those superconductors, which really penetrates across the integer filling positions, is now being interrupted by the correlated insulators. So basically, after we had those findings, of course, the narrative was that these correlated insulator phases and the superconductors maybe are not as connected as we originally thought. So it looks like changing the dielectric environment somehow affects the insulators quite dramatically, but it does not have such a big effect on the superconductors. And I think one way, of course, to take it is that, this is exactly what you would expect from an electron phonon superconductivity, that, it just should not be affected when you change the dielectric environment, or it should be very weakly affected. But of course, I think there are, of course, many different scenarios people are debating. So, of course, correlated, so sort of superconductivity arising from correlations is not ruled out completely by these results, but I think it just enriched a little bit the debate. Okay, so I will now just show a little bit of the topological results, probably the last thing I will show. So if there are any questions about superconductivity, I think maybe this is a good time to ask now.
I have a question about the density of state peaks you showed like 2 slides ago.
Yeah.
Are they due to saddle points in the energy momentum dispersion?
Sorry, this one?
Yes.
Yeah, exactly. So this the density of states peaks, they're basically roughly speaking, they're in the center of the band. Roughly.
But is it a Van Hove singularity?
Yeah, exactly. Those are exactly those are Van Hove singularities. Yeah.
No, but are they associated to saddle points in the energy momentum dispersion?
I don't.
Because when 2 direct phones hybridize, they form saddle points.
Right. Yeah, they're exactly associated with the saddle points. Yeah.
Okay. Thanks.
Yeah. Mm-hmm. Okay. So all right. So then and then I also want to mention, this is a little bit of a gear change now. So this story was about correlated insulators and superconductors. But I really want to also mention the topological magnetic states. So basically, what we also see in the very same devices, and we really see these features. So we really see these features quite robustly now. Is that we see very close to zero magnetic field, and actually other groups, actually including us now. There's a paper in preparation now. We also see those states at zero field, so basically at zero magnetic field. We see Chern insulators, and basically how Chern insulators manifest itself on our measurements is that we really observe regions of quantized hole resistance, which is quantized just to h over e squared, and basically usually the exact quantization value depends on the integer filling of electrons per molar site, which we choose. So really, we observe these Chern insulators with Chern numbers 1 originating from a filling factor of 3, and we observe Chern numbers of 2 from filling factor 2, and we observe Chern numbers of 3 from filling factor 1. So, and just to give an example, so this is a typical measurement of one of those Chern insulators. And basically, what you see here is this point here. This is basically exactly how filling. This is minus how filling of the valence band. So this is a filling of -2. And you can see that really, depending on a magnetic field direction, we really get these perfectly quantized regions. So if you really take a cross section along this line here, this is this measurement on the right, we really see that Rxy is quantized to h over 2e squared. And again, this is a filling factor of 2, so this is all consistent. And Rxx really is almost 0. So again, in as expected from a quantized Hall conductance. So basically, as expected from edge transport. And of course, further evidence is that this shaped region here, of course, it also has a slope in a magnetic field. So in the dn over dB diagram, it also has a slope consistent with a Chern number of 2. And basically, the ongoing picture. So this story is now probably the one story which is fastest developing. So I haven't introduced the data in this talk, but we have a paper on arXiv which really shows these features in much better detail. And then there's also the group of David Goldhaber-Gordon, the group of Andrea Young, and also Ali Yazdani had a paper recently on all those features. And basically, the conjecture is the following: is that we think that there is really strong symmetry breaking in the system, and basically that we can think of the flat bands as consisting of degenerate systems of Chern bands with Chern numbers 1 and -1, and basically depending on the filling of those bands, we can get all the different Chern numbers in the system. So we can get basically bands with Chern number 3, 2, or 1, or -1, or -2, or -3. And basically, whenever to open up a gap between those bands, then we basically need interactions, or sometimes magnetic fields can break up bands, band gaps, can make band gaps between those bands, and then we observe these quantized Hall conductance region. And and basically these states, because of often their valley symmetry broken and the Berry curvature is non-zero, the electrons in these bands really behave like they have circular orbits, and basically because of that, the system is also magnetic. So we really believe now that those are orbital ferromagnets which live in the bulk of the system, and then we have also topologically protected bands on the circumference of the device. And as I mentioned, so this this type of physics really lives in the same devices. So in principle, now we have a platform where we have topology, magnetism, superconductivity, and correlations all in one system, all gate tunable between each other. And I think the field is just in the very beginning, and I think we're excited to see how we can explain all of this in the near future. So I think with that, I think I want to wrap up. So I just want to I'll skip over a bunch of things. But I think I want to thank my group again, and I think I want to thank you for your attention.
Thank you, Dmitri, for this nice talk. So if anyone has any other question, please feel free to unmute yourself and ask.
Dmitri?
Yep.
So I think you mentioned the quantum sensing using TPG. Can you briefly elaborate this part?
Yeah, so right, so basically this is actually right, so this is why I actually made this graph with the thickness dependence and the density dependence. So basically there is a whole field which is actually commercialized now of superconducting detectors. And superconducting detectors, in particular single photon detectors, are basically one of the most sensitive detectors of quantum light right now, and they're used in all quantum optics laboratories at this point. And these detectors depend on the heating of the superconductor. So basically, if you have a very thin superconductor and you absorb a photon, this photon can heat the superconductor and make it resistive, and therefore you can detect a photon. And basically, the ideal material for such detectors is usually the thinnest possible superconductor you can make, and also the superconductor with the lowest heat capacity. And heat capacity is basically proportional to the amount of carriers. So basically, it's proportional to the amount of particles it shares its energy with. And so in this regard, graphene is almost the ideal platform for such detectors because it's the thinnest superconductor by far, and it's also by far the superconductor with the lowest electron concentration, and therefore the lowest heat capacity. So we have a paper on actually it's published on Nanoletters where we discuss such detectors, and basically we find that these detectors could work in the terahertz and even the gigahertz, at least theoretically.
This is using TPG, right?
This is magic angle twisted Bilayer graphene. Yeah.
I see. Wow, cool. Thank you very much.
Question?
Yeah.
Actually, more of a request, because you showed a lot of slides very quickly, and I think they show a lot of really nice applications. So, I mean, if other people don't have more questions, perhaps you could, show those slides to us.
Okay. All right. Okay. So this one. Okay. So we have a paper which should come out October 1st. This is actually in collaboration with Casey Fong and Dirk Englund and Philip Kim. And this is actually a paper which was still in development when I was at MIT 3 years ago. So this is a Boston, so those people are all in the Boston area. And so what we, along those lines, which I just discussed, so low heat capacity, superconductivity for sensing. So what we did is with led by Casey Fong, before even we knew that graphene can intrinsically be superconducting, we made graphene quasi-superconducting by making Josephson junctions by basically proximatizing it with niobium nitride or niobium. And basically, we already made detectors then based on this platform. And so basically, this is a detector concept which we have. So we can, we incorporated the graphene JJ. So the JJ goes in this direction. So we can send a supercurrent across the graphene in this direction. And this is basically the IV characteristics of the supercurrent. And at the same time, we were able to integrate it to a quarter wave plate resonator, where we basically can inject gigahertz photons onto the device. And so basically this detector concept really showed the, without going too much into detail, I just showed the outcome. So basically this detector concept resulted in noise equivalent power, which is basically the detectivity above the noise floor, which is in the attawatts per square root hertz. And this really, this ultra low noise equivalent power, this really corresponds to the ultimate limit of how good a detector can be. And so basically, this is basically right. And if one now converts it into photons, then really what we were able to show that it is sensitive enough to detect single gigahertz photons of 32 gigahertz. So this is really, I think, the first demonstration that a detector can be used, a click detector, which can be used to detect gigahertz photons. And of course, because it was incorporated in this quarter wave resonator, it had a ultra high quantum efficiency of 99%. And actually, there's a second paper coming now where we actually perform it as a click detector, so we can show that single photons really can be sensed with this type of detector. So bottom line is, I think we start and realize that graphene can be actually quite useful for quantum applications, in particular quantum sensing. Right. So I think this is on the detector side. This is mostly it.
You had a couple more slides, I think.
Should I? I mean, I can like.
No,
yeah. I mean, this is.
I have a question before that. So I guess, do you expect circular dichroism for this orbital ferromagnet?
I probably am not such. Yeah, I'm not such a big expert on that topic, but yeah, I'm not sure.
Do you have
Yeah,
any?
I'm not.
Do you have any idea about the optical spectroscopic signatures?
Yeah. So so okay. So I think so I mean I think because it's valley symmetry broken. Of course, if you sort of do some circular light polarization experiment, circularly polarized light experiments, then you should be seeing something. I would imagine similar to what people. I mean, probably you could see valley Hall effect or something like that. But to be honest, so one disadvantage of the system for optics is that the bands are ultra flat and ultra close to each other. So I think it's very hard to excite only one band, but you're actually exciting immediately many bands in the system. So I think if you want to study just the flat band itself, I think it's probably quite challenging with optics. But I'm not such a big optics expert, to be honest.
Can you say something about magnetic properties? So can I ask a question? Can you say something about magnetic properties, especially of correlated insulators, but maybe also as other doping levels? What is known about magnetism, eventual magnetism of these states?
Yeah. So I mean, so the ongoing interpretation, and I think don't have a full understanding of it yet, is that probably valley symmetry breaking is the dominant driving force. So I'm not sure if we really think that spin ferromagnetism is happening, but I think most of the time we think it's really the valley which is driving it. And in terms of valley, this is also why we think it's orbital ferromagnetism, because this would be consistent with valley symmetry breaking.
In spin ferromagnetism or other type of spin magnetism, it doesn't exist, or no indication yet?
I think look, I think it's a matter of interpretation at this point. So there is no clear evidence for a spin ferromagnetism in the system, but there's also no direct measurement of orbital ferromagnetism. It's really in the interpretation, and I think theoretically, the sort of the people who I refer to are people like Alan MacDonald. He's really believing that it's a valley symmetry breaking, and it's really orbital magnetism which is happening in the system.
But at least in correlated insulator state at low temperatures, there should be something with spins or orbitals, or maybe with both.
Yeah, so I think that's right. So in principle, both symmetry breakings are possible. So we can have spin degree or spin symmetry breaking, specifically for the odd integer cases, like for a 1 electron per unit cell. Of course, we could imagine that the spins just align ferromagnetically or even antiferromagnetically. This is all possible, I think. But I'm just probably repeating what I hear in conferences at this point. I think the whole debate is about valley symmetry breaking at this point.
Okay, thank you.
Yeah.
I have a question, if I may ask.
Mm-hmm.
Yes.
So early on in this game, maybe a year ago or more, they talked about some strange transport behavior in the normal phase above the superconducting temperature, something like a Planckian dissipation, linear resistivity, similar to cuprates. What's the status of that at the moment?
Yeah. So this I think this curve basically demonstrates it a little bit. So basically, I think what you're referring to is above the superconducting transition, the temperature dependence is kind of more or less linear, right? And basically, there were initial comparisons. So initially, some people were really trying to draw direct analogies to the cuprates. And of course, looking at this linear temperature dependence, this could remind you of a strange metal phase, like the one observed in the cuprates. But then actually other groups were also explaining these results just by electron-phonon interaction. So I think it's open question at this point. I think at this point the most voices I hear are that it's neither simple electron-phonon interaction nor it's a strange metal.
But can you explain in many other materials where they claim to have seen this strange metal behavior? They claim was that even simplest estimates of phonons could not even get close in order.
No, so here we get close. Here we get close.
So can you explain why can phonons do the trick here and not somewhere else?
So okay, so the thing is, so basically in graphene we have actually this was my PhD work when I was still at with Philip Kim. Basically in graphene you typically have a very small Fermi surface, and therefore in graphene you have a very strongly reduced interaction between electrons and holes. Between electrons and phonons. Okay, just because the energies of the phonons and the energies of the electrons on the Fermi surface, they don't really match. And basically, therefore, the characteristic temperature in graphene is usually not the Debye temperature when you look at phonon energies which contribute to the transport, but this is the Bloch-Grüneisen temperature, which is which can be orders of magnitude smaller than the Debye temperature, and therefore, in principle, in single layer graphene, we observed linear temperature dependence of resistance up to 100 Kelvin or so. So it is not completely unusual to see linear temperature dependence in graphene, again, because of this, because it's defined by the Bloch-Grüneisen temperature. So in principle, also, if you do estimates of the slopes, I think what's really important, right, in this whole debate is the slope of this temperature dependence. If you do estimates from just a very simple electron-phonon interaction, this was done by the Sarma, for example. This was this theory which was used in previous work. Actually, you get relatively close to this linear temperature dependence. So you actually get a factor of 3 or 4 close to it. So you're not factors of 10 off to describe the slope. And so some of the other theories which I was hearing in the so for example is that because you have now this mini brilliant zones and you have this Moray interaction, Moray lattice potential. So for example, people expect that Umklapp scattering could be much stronger here, and that would basically amplify the electron-phonon interaction, and then it maybe would actually explain this high slope here. So I think right. So I think this is I'm just repeating what debate I'm hearing. So I'm not an expert on strange metals, so I'm not sure what's going on in the strange metal theory, but I think at least from what I know about graphene electron-phonon interaction, it's not completely ruled out that that could explain the whole story here.
Okay, thanks very much.
Can I ask a question? Could you comment on any possible connection between the orbital magnetism observed in your devices and the Pomeranchuk effect that, for example, UCSB and MIT Weizmann recently reported?
Yeah. Okay, this is a very that's right. So I'm also at the stage of reading the papers. So right, so I'm your question is about the papers which appeared a week or two ago in arXiv, right? And it's quite of an exotic effect. So I think what the Pomeranchuk effect is that somehow you get an ordered phase by increasing the temperature or something like that, right? But yeah, so to be honest, I'm not an expert on these papers. I have to read them myself first.
Okay, thanks.
This is very you're at the frontier. You're at the very frontier of the field if you ask those questions.
Any other question? Well, if not, let's thank Dmitri again for this nice talk, and see you all next week with Teresa Paiva. Bye-bye.
Okay, thank you. Bye-bye.